Today, I'm making the wild claim that pi can equal something other than its known value, and the even wilder claim that it can equal something erroneously attributed to it in the past. But rather than deny my mathematical background to make the claim, I will embrace it instead. First, we start with the familiar definition of pi. Whenever we work in flat 2D space, we construct circles as the set of points equidistant from a center point, and a diameter is a straight line that cuts through the center of the circle. Because of these particular properties, the relationship between the circumference around the circle and the diameter that cuts through it is always a fixed number. We call that fixed number pi, and in flat space, it is always the same. But in a space that's not flat, the diameter may actually be extended. Draw a circle around a mountain, and the diameter that goes up and over that mountain will be a lot longer than a diameter that goes through a circle drawn around a flat plane. That should be pretty intuitive. Okay, now that we know that the relationship between circumference and diameter, also known as pi, can in some circumstances be different from its usual value, how do we ever get it to be exactly 3? If we have to construct a special space, what special space do we construct? Here's what I propose. Note that we're going to use plain old regular Euclidean geometrical rules with no weird stuff until I say otherwise. First, dig a hole in the ground the exact shape of a half sphere. It may be easier to put a bowling ball into a box and fill it with cement exactly to the halfway point, or preferably a much bigger, perfectly spherical object, if you can find one, to make potential future measurements easier. Call the radius of the spherical object a distance of unit 1 for simplicity. 1 is equal to a half a diameter of a chosen spherical object. If you used such a spherical object, remove it to have your perfect half-spherical hull, or as perfect as we can get it in the empirical universe. When you have the hole, put a plank across its diameter and measure an angle into the hole exactly 30 degrees off the plumb line dropped to the center of the hole. Mark the surface of the hole where this angle leads. We'll call this step 2, since this is pretty much the second thing we do after actually creating the hole. Note that a full 360 degrees is 12 times the 30-degree angle we used in this schematic, so the arc cut by this 30-degree angle in our flat normal Euclidean universe schematic is equal to 2 pi over 12. Repeat this process on the other side to make another 2 pi over 12 arc. Next to each other, these form a nice arc with a length of 4 pi over 12. This will be important to remember later. But now, let's go back to step 2 on our earlier schematic when we only had one 30-degree angle. We can see we've essentially created a 30, 60, 90 triangle with the longest side being 1. These kinds of triangles have a 1, 2, square root of 3 relationship, with the longest side being 2. Only since our triangle's longest side is 1, we really have a 1/2, 1, square root of 3 over 2 relationship. So the bottom of this triangle has value 1/2. Next, we'll go to step 2 again. But this time, we want to repeat step 2 many times, rotating slightly around the hole in each step and marking the 30-degree angle in several places, enough times to form a circle near the bottom of the hole, shown in green here. This green circle will have a radius of 1/2 and diameter of 1. This gives it a very simple circumference of plain old pi. Not 2 pi as we're used to seeing. Remember this plain old pi. It will be important also. Now I'm going to zoom onto the relevant part of what we're doing here so we can see it better. Notice the 4 pi over 12 we were supposed to remember was snuck back into the schematic where we originally calculated it to be. And now we're going to use that 4 pi over 12 and that plain old pi I said we had to remember. Notice this 4 pi over 12 arc connects 2 points on the circumference of the circle, which we found out had a circumference of pi. And now we finally reached a point where we can get weird and non-Euclidean. We can think of the arc of 4 pi over 12 as being a new, longer, quote-unquote diameter of the circle we made with circumference of pi. After all, the circumference we've drawn is on the 2D surface, and this 4 pi over 12 diameter is also on the 2D surface, as opposed to the 3D space Euclidean diameter, which is floating around in the air. So if we think of this 4 pi over 12 as the quote-unquote diameter of this circle drawn in our half-spherical hole, the circumference over diameter relationship of the circle is easy to calculate. It's simply pi over 4 pi over 12. We can call this particular circumference over diameter relationship pi star, and we can reduce it using the old flip over and multiply algorithm of dividing fractions to get pi over 1 times 12 over 4 pi. The 12 over 4 cancels to 3 over 1, and more importantly, the original pi's cancel out, which beautifully simplifies to the simple number we're looking for, 3. So pi star is exactly 3, not 3.14 or any approximation close to that. So now we've shown a process that, hopefully, if I did my algebra and geometry correctly, should get us a circle with a circumference to quote-unquote diameter relationship exactly equal to 3 and not a number close to 3.14, but only in this very specifically constructed space. And hopefully the process described can be tested empirically by anyone curious and not lazy enough. I'm too lazy to physically build an apparatus like the one I've described, making half-spherical holes and doing measurements and such. I majored in math specifically to avoid such experiments, which is kind of sad, I guess. Of course, if someone says that pi is not simply a diameter over a circumference in any space, but explicitly a flat diameter over a flat circumference in a flat space, then of course this different kind of pi we constructed with longer quote-unquote diameters in a non-flat space will never gain any type of acceptance, and maybe it shouldn't. I imagine circles might start to look really weird if they're defined in any 2D space as the collection of points equidistant from a center. Variable pi's might be the least of a geometer's worries.